Sun path, yes, it is very vital for a building. When you have a mass development like a campus or a city, the sun path analysis is required to talk about facade and shading, how much is overhanging required, then kind of windows, how much is the self shading, how you can see the building impact from the neighboring building, how the shading is having impact, and at site, how these individual buildings are overshadow effect is happening. So, sun path is critical for any building. When you have multiple development, you can have you will have benefit in doing all this by doing a sun path analysis. It sets the tone for the building right from beginning. You can look at this picture, how this study has been carried out. One is the heat island effect. You can see the heat from the surfaces when you build this like a small concrete jungle, how the heat island effect and temperature rise around the building is happening. And overshading, you can see the how this buildings are giving the benefit to the adjacent building, how the shading is happening to the different building from building to building. So this also can be studied. Moment you have this master plan ready with the building element, and you can little bit adjust your orientation and get the best out of these kind of campus design by doing overshadow from building to building and get benefit out of it. And this shadow pattern you can study like 9 a.m., 12 and 15, how the sun angle is moving and the shading is getting shifted from one place to another. Slowly you can see which direction it goes. So ideally we have to study for the worst day in a year, March, April, few days we have to study and see how this is having impact. At the same time you can study the energy performance of the building. When you have a shading happening from one building to another, the energy consumption for this building is coming down, and when you don't have any kind of shading, you can see the building consumption goes up with the same occupancy and load. So that gives an indication how this shading and sun path analysis is helping you for understanding your energy performance of the building. And daylight is very, very vital. We normally 90% of the life in a day we sit indoor, either at home or in offices. So we are very comfortable, or our productivity goes up when you work in outdoor environment. That's how the human beings are brought into this world. So we like to have more and more daylight inside. So possibly we should have more daylight but not glare. This is where we have to really balance both daylight and glare. So the facade design and facade element plays a major role for glare. Just by having a glass you get the daylighting, but glare cannot be arrested without facade design. So this is very vital to balance both parameters to get the beautiful daylight indoor spaces. Now the glazing areas, if you look at where how much is the glazing area, depends on your the projection angle and type of facade kind of orientation, you can get the glass fixed for a particular facade. And very important thing is, when you have a glass, though you have shading devices, whereas the daylight penetration on the perimeter will be little higher always in terms of 1200 lux you can see here. But this is little strange for a occupant sitting in the facade of this area or adjacent to the perimeter area. So we prefer to have some sort of light shelves to deal this excess daylight penetration here and put this daylight, concentrated daylight on the perimeter to the interior space by providing light shelves. So light shelf will effectively help us to minimize the some sort of discomfort or excess light on the perimeter and allow this excess daylight to be penetrated to the interior space where we have an artificial light. So in addition to your facade fins, we need to have the synchronized design of light shelf to penetrate daylight to the deep interior to minimize the discomfort for the occupant on the perimeter. At the same time, increase your daylight penetration to the interior spaces to optimize energy performance. This is one more analysis in terms of how the relative heat gain for a particular facade and with the type of glass what you have selected. So you can have multiple glasses and parameter, like if it is SKN 154, which has got 0.26 SAGC, and ST 120 about 0.22. By looking at this, people will definitely go for 0.22 per energy. When you look at daylight, people get into 50%. But this is, you can't do it just manually in random basis. You have to see how this glass is having impact on the particular facade, and this one having impact both on energy and daylighting. And if you look at heat gain, then SKN 154 is about 240 watts per square meter relative heat gain. And when you use the same ST 120, just 190, because this SAGC is more. So this also gives a relative heat gain, gives some direction for us to choose a particular class for a particular facade. So relative heat gain analysis is vital in addition to daylight analysis for a selection of glass. So this project, they have gone for a separate vision glazing for a different, for north and south SKN 154, because I need more daylight from north, and east we reduced to 18% daylighting VLT with more stringent glass. Then we have a view glass and daylight. Daylight glass we have gone for even more on the upper portion of your wall, where you get a more daylighting, and view glasses vision glazing is little more stringent, so that you will avoid glare as well as heat gain. So two layers, little relaxed one for the upper portion of the wall, get the daylight penetration without blind, and lower portion will be little better efficient glass. So in that way you can optimize the daylight and glare for an indoor environment. Now this is a simple one, like how the daylight is penetrating to the interior spaces, and you can do this with the Dialex and various softwares available to understand the lux level in your work plane from different facade. So these are the areas we have a daylighting, and you can understand the lux level here. So this also helps you to get into the glass selection, depends on, and if you have a more daylight penetration, suppose here you have a 640, suppose you are getting 1000, 1200, you can put a light shelf and make this space also a little more daylighting. So this gives a design direction for you after doing the daylight analysis for a particular work plane. Then you can get into your shading depth as well as light shelves and its impact on your building overall performance. And the last important analysis before you get into the selection, the glare analysis. Recently you have a WELL rating, and even LEED version 4 is really directing towards this direction of how the window should be positioned. Depends on the window to wall ratio, the glare control devices needs to be implemented, which is be automatic control. It can be like a blind, and also the angle in which you place your computer working about 200, I think about 120-degree angle from the facade, wherein you will get a less glare. So every computer, every workstation on the perimeter where the daylight penetration is there need to be focused and adjusted. You can't have a uniform design for the interior space and work spaces on the perimeter. It should be angled such a way that the glare is completely arrested, so that person sitting on the perimeter area will have less strain on eyes and working in the computers. So this is a new dimension is given from the WELL rating program, and now started practicing this in your in majority of the building design and construction in this country. So this is going to be ruled the interior design for most of the building. Very vital when you look at the building occupant comfort and their productivity and health. So basically, to look at overall, when you look at conductive heat gain overall, if you want to estimate how this facade is performing for me, how much is the heat gain from this facade, first you start with heat gain from wall, plus heat gain from the roof, then heat gain from glass. So overall you look at your building envelope, how this is having an impact on your overall heat gain. So you need to focus on wall, roof and glass. All three put together, if you try to reduce this number, conductive heat gain to minimize this heat ingress to the building, then you can really work on your active components to save energy like air conditioning, lighting and equipment. This is how the building has to be approached. Less conductive heat gain for the building element, then efficient active element to reduce overall energy performance and provide better performing building. This is another project where we set a tone of the relative heat gain. If you go back to the previous slide, you can understand conductive heat gain. So we set a target. Normally in India, if you look at building, it will be around 2 watts per square meter. Here we set a tone of basically target is 2 watts per square feet is the Indian numbers normally we get. Now here we set a target of 1 watt per square feet is the conductive heat gain to the building. Then we started doing various combination of wall, roof, RCC 75 mm, overdeck insulation, SRI paint. Then we reduced to 25 mm. Like this we have gone with the roof, different kind of roof, and what is the U value of the wall, then what is the maximum conductive heat gain, window to wall ratio we changed, then if it is 20%, if it is 35%. So we keep changing the combination of different elements, roof, wall and window to wall ratio. Then we thought these three options, these are the options we created based on the material and technology available. Then these 3 options are meeting these other 4 to 8 which are going beyond my target of 1 watt. So without doing this, you can't have the understanding of your building as a whole, how the conductive heat gain or relative heat gain is having impact on your building. So you need to bring this kind of chart in the beginning, select best suited wall, roof and glass option for you to get this overall conductive heat gain below my target. So this gives a direction or gave a direction for the design to go with one of these 3 options and eliminating these 5 options from the shortlisted design. So this is how the approach should be for a building in terms of how the building can be designed to get the maximum operational efficiency. And you know very well the HVAC design having direct impact from the facade. So you need to work on the once you know the heat increase and you have optimized with the facade and window to wall ratio and the different element on the facade, then you can look at how do you optimize this cooling. Keep working on the cooling and see how we can bring the cooling down for our tropical country. Then you adjust your facade accordingly. There's always a saturation comes. Beyond that, people can ask, instead of 600 mm, why not 1200 mm Sarja, or why not 2000 mm? But beyond certain limit, saturation occurs. So you have to stop with that, then get into the cooling design so that you can optimize overall cost. This is a very interesting slide in terms of how this solar heat gain coefficient having impact on your HVAC kilowatt hour consumption, overall energy. I'll straight away come here. This is 60% window to wall ratio. I gone with 0.2 SHGC. This is the best class available. So 60% and 0.2, if I get into the window to wall ratio of just 30 or 40%. So one is 60% window to wall ratio, another one is a 40%. When you have a more window to wall ratio, I need to go for more stringent glass where the glazing area is more. And when I went to 40%, I relaxed glass from 0.2 to 0.25 to get the same level of energy consumption. So by relaxing my glass, reducing window to wall ratio, I am maintaining the same level of energy consumption to the building. So this is the direction in which you can optimize your window to wall ratio and relax your glass. More the glazing, more stringent required to optimize your energy. If less window to wall ratio, and you can really optimize your cost towards initial investment on glass. Similarly, 50 and 35. So this is the balancing act you have to do for a building design, looking at the window to wall ratio vis-a-vis the SIGC and energy consumption. You set the tone for energy consumption. It can be 90 EPI or energy performance index. It can be 90, it can be 120. So moment you have that number, then you can play with the window to wall ratio and glass specification and look at how to optimize your overall the energy and also the initial investment. This is another very interesting project we did in Noida. Though the standard says how the various glasses we selected for building, how this has got an energy consumption impact, how much is the reduction, what is the percentage reduction, how many point in lead they achieved, and what is our preference. So this, in addition to your procurement guide doing the selection based on the cost, this gives a direction for them which glass. Suppose this guy is getting the best glass out of this and getting the L1, that is the best one to choose. So we have given our preference 1, 2, 3 not preferred. So this guy gone with the preferred one glass at lower cost. This preferred one glass, it's even less stringent than the standard. 0.25 is the standard for India, ASHRAE standard. I went in for 0.38. That means relaxed specification. Reason is one very critical factor to be seen here is this building has got a 45% window to wall ratio, out of which 65% glass sitting on the north facade. That means this has got a beautiful design wherein I can go for relaxed glass from the standard to get the best performance in terms of 28% and energy reduction overall I am talking about, and about 0.73 from the base case, and I am getting all 6 points required. Then why I need to go for stringent glass 0.25 or 0.26 where the energy difference is hardly anything, 28, 28.73, 76. So there is no major difference. I relax the glass to go for 0.38 to optimize the overall investment cost without compromising on the energy performance and daylighting. This how the balancing of heat, daylight and energy parameter to be considered for a building. So you need to have more and more analysis, varieties of glasses, and here also you can add wall and roof, and overall you can see the performance. This is purely on the glass selection. This is another building, this is a government building. We did this with around 450 lakhs investment, and payback is the 3 years. Just optimizing the conventional building into proposed and keep changing the parameters. Chiller we kept same thing, added heat recovery wheel, daylight sensor got added, and this glass was VLT of 21%, SIGC 0.2, and whereas here SIGC is 0.25. So we started optimizing it. LPD 0.8 watt per square feet, and initial design was 1.3 watts per square feet, and similarly roof, wall, everything we thought this is what the proposed building. Then we started doing various iteration to see how we can optimize it. So we played between both, and with 450 lakhs additional investment gone into the building, and they got it in 3 years. In fact, this was the predicted energy performance with the payback by 3 years. Actual case we studied for 1 year operation, it was just 2 years to 2 months. So that was the level of benefit you get when you do the optimizing of your proposed building, not merely going with the standard, and you have to balance between standard and what is really actually required for a building. So in a nutshell, if you look at any building for that matter, you have to look at various parameters. You can't only look at aesthetics, or you can't look at only the occupant comfort or energy performance. Of course, you need the rating, but rating should not be the driving force for the building design, and less complicated to operate. Tomorrow you can't bring some system which brings a lot of complication for the occupant or operators to operate, then they will bypass. You need to have an ROI to make it sustainable. It should be easy to maintain, and it has to be monitored and reported in terms of performance. Very, very vital. Otherwise, the sustainability will be on the paper only. And also, we have to look at operation needs, what they want from building. And you need to have a people operating. Buildings should be properly trained and hand over the system to them to operate. And also the maintenance. They should be easy to access the building equipment to maintain. Otherwise, they will leave it for long and it doesn't give the required performance. And suitably for the project. So you have to adopt the technologies. Yes, you need a proven technology, but the technology is adapted suitably for the project. You can't bring some system which is not suiting for the particular operation. Sometimes you require a VRF, sometimes you require a window ductable split with the fresh air provision. So it depends on you can't have a centralized system for all the building when you have only 10,000 square feet conditioned space. So accordingly, you have to select the system suitable for a particular project, looking at all these parameters when you take a project for design. So to sum up, ladies and gentlemen, I always prefer about 30% glazing. I am deviating little from the standards. Though ECBC and ASHRAE is 40, glazing 30% non-north, less than 30%, and north you can go up to 40, but overall you can achieve this 40%. And I prefer not 95% daylighting, which increases the energy consumption in the building. Looking at the current design of say 20,000 square feet, 25,000 square feet floor plate, I think about 60% is ideal number to achieve. You can balance. Definitely you should look for 90% views for the building occupant to the exterior, more and more open office culture, and minimize the cabins and enclosed spaces. It can be in the middle of the building floor plate, not on the perimeter, which controls or arrests the heat daylight penetration to the interior spaces. And prefer to have a daylight and view glazing, so that you can avoid glare and get the daylight for the entire day. And shading to minimize the glare on the non-north. So you have to have a shading devices if you have a glazing of 40% and more. Light shelves to avoid discomfort to the perimeter area where excess daylight penetration. You can have a light shelves to get this daylight from perimeter to deep interior where people are not having daylight. And roof with the overdeck insulation to arrest the heat getting into the building before it hits your body. So we don't prefer underdeck insulation. Overdeck is better to arrest before heats up your building. And also you can have a green roof or reflective tile for the roof. And overall heat gain should be set at less than 1, around 0.9 watt per square feet. And the energy performance index for our kind of climate, about if you have a cooling, about 100 units per square meter per year. And there are many corporate achieving 80 and 70. So ideally overall we should look at less than 100. These are the around 9 very important parameters for a building design. If you look at these numbers, and your building will be really super performing. In addition, you can go for solar energy to substitute, make it really sustainable for long run. So ultimately we have to look at lower first cost and lower operating cost. This is like very critical parameter to be considered in the building design. Right from beginning, set a tone that I will invest where there is an ROI. I will invest where my operating cost is going to be less. I invest where my occupant comfort is taken care. Health and well-being is taken care. So you have to balance your investment and operation cost. If you do the OPEX and CAPEX well balanced, and sustainability will be very good economic option for anybody to adopt. So with that, I thank Class Academy for this wonderful opportunity. I hope the listeners and viewers are getting benefit out of it. Thank you so much for patient hearing.